Supervised learning. I'm in the BigMart file because this algorithm is both regression and classification. Supervised learning, regression, or no, we will go into HR analytics. Okay? HR analytics, because we are going to talk the classification model first and then the regression model later. Supervised learning, classification, tree-based algorithms, single tree model, decision tree. Single tree model. The output is one single tree. Decision tree model. Both regression and classification. The algorithm works both as regression and classification. Also used in unsupervised learning as part of output, feature or variable importance is provided. Single tree model, decision tree model, it's both a regression and a classification model. It is also used in unsupervised learning because as part of output, you will get variable importance. You will get feature importance or variable importance. So decision tree is a single tree model. The output is a single tree. The output will be a tree. The output will be a tree model with root node, decision node, terminal or leaf node. The output will be a tree model with root node, decision node, terminal node or leaf node. Tree is read top down. Tree is read top down. You should start reading from top down and easy to interpret. Rules are created from tree and these rules are used for prediction. Rules are created. Rules are created from the tree and the rules are used for prediction. I will show you how the rules work using when age is greater than 50 and gender is equal to male and his profession is what you call salaried, he will buy the product. Buy is equal to yes. So such rules are framed and these rules will be used for prediction. So decision trees are easy to interpret. They work with large scale data. They also very, very important, easy to run. They don't need much computing power. They're very, very easy to run. Now let us look at the tree splitting methods. Tree splitting methods, there are many of them. The popular one is Gini method. What is the formula for Gini? 1 minus sigma sum of probability of I square. 1 minus sigma probability I square. 1 minus sum of probability square. Gini method. Lowest Gini is first split and ascending order. Lowest Gini is first split and ascending order till 0.40. Lowest Gini is first split and ascending order. Next lowest till 0.40. Gini greater than 0.40 dropped from the tree. Variable dropped from the tree. If a variable's Gini is greater than 0.40, it automatically eliminated from the tree. That is how variable importance is detected. The second method is entropy and information gain method. Entropy and information gain method. Entropy is equal to minus sum of probability of I into log probability of I, comma 2, log second base. Log second base probability of 2. And information gain. Information gain is equal to entropy of dependent variable minus entropy of variable. Entropy of dependent variable minus entropy of variable. Highest information gain is first split and descending order till 0.50. Information gain less than 0.50, variable dropped from the tree. Variable is dropped from the tree. So these are the prominent splitting methods which are used in machine learning. There are many methods. There is one method called shade, chi-square based method, Bayesian methods are there. But in machine learning, we use both in Python and R, we use Gini and entropy. Default is Gini. Default is Gini because it is easy to calculate. If you want to use information gain or entropy, you have to give it as an argument, both in R and Python. Because both in R and Python, default is Gini. Default is Gini. Okay, tree splitting methods, very important for us because not much of a difference is there. Large scale data also we tried. I tried with both the methods. I have not seen much of a difference. Decision tree works well with missing values, with skewness, kurtosis, and outliers. Decision tree works well with missing values, skewness and kurtosis, and outliers. Compared to the basic algorithms, multiple linear regression and binary logistic regression, which are highly sensitive to skewness and outliers, decision tree is less sensitive. Decision tree is less sensitive compared to the parametric algorithms, multiple linear regression and binary logistic regression. So decision tree is a non-parametric algorithm. Non-parametric means what? No prior assumptions. There are no prior assumptions, where we have 6 to 8 assumptions in linear regression and logistic regression. Remember, there are a lot of assumptions we have to, then only we will get a good fit model. We don't have such assumptions with decision tree model. It's a non-parametric algorithm. It is less sensitive, or it is impacted less by the missing values, skewness, kurtosis, and outliers compared to the MLR and the BLR. These are less sensitive. The only disadvantage is overfitting. The only disadvantage is overfitting. By default, decision tree model will overfit, and it must be controlled using max depth of the tree. Using the max depth of the tree, we will control the overfitting, because it builds a very large tree in the backend. It builds a very, very large tree in the backend. So the chances of it being overfitting is very, very high. Very large trees are built in the back with multiple sub branches, multiple sub trees, huge level big trees are built. Now, these trees are prone to overfitting, which can be dealt with by using the max depth in the argument as an argument. By controlling the depth of the tree, we can control the overfitting. Okay. Now, for decision tree, the library is RPart. Oh, I forgot the important thing. Recursive partitioning. One second. Decision tree is recursive partitioning and binary splitting tree. Decision tree is recursive partitioning and binary splitting tree. Recursive partitioning the node splits on the previous node number of observations, and once all observations are classified into terminal nodes, tree growth will stop. The tree growth will stop. So recursive partitioning trees. That means it will split on the previous node number of observations. The previous node number of observation is what it splits. So as the tree goes down, the observations are classified into terminal nodes. Once all the observations are classified into terminal nodes, the tree growth will stop there. So library RPart is an inbuilt library, so you don't need to install it. RPart is an inbuilt library, you don't need to install. You need to install one library for visualizing the graph, what you call the tree, rpart.plot. Install this library, rpart.plot. It's a very smart library, small library. Library rpart.plot. So RPart is an inbuilt library. You should no need to install. It is there. Just activate the library. But you need to install rpart.plot. Okay. Now, HR rpart is equal to rpart is underscore promoted tilde dot comma data is equal to HR train df. HR R part is equal to R part is underscore promoted tilde dot comma data is equal to HR train DF. Summary HR R part. Summary. Oh, we have a problem. It is taking as regression, so we have to give as dot factor. See, mean square error is calculated for regression. See here, we got mean square error. Mean square error is for regression. So it is treating it as regression, but actually it is classification. So we have to add another thing called as dot factor. Because in classification, what we get probabilities. We get probabilities. Now you got the probabilities. Okay. So as dot factor is underscore promoted tilde dot data is equal to HR train DF. So you can see, right, variable importance, only average training score is important, 100. See? And it is explaining each and every node. Here, it is a very small tree, but in the other data sets, we get a very large trees. R part dot plot HR R part. So it's just giving us a very small tree because of the data really being highly imbalanced. It is giving us only one level of the tree. R part dot rules HR R part. So as a one, it has only one rule. The probability is 0.08 when average training score is less than 91. The probability is 0.88 when average training score is greater than equal to 91. What error? Comma you give tilde dot comma. Did you close bracket after is underscore promoted? Yes, sir. And there is a bracket after HR trained here? Double bracket. No, single bracket. It's a bracket error. If you're saying unused argument means the bracket error. What's the name of the paper? ROCR is for AOC, receivers operating curve. Area under the curve. If we didn't install, okay, no problem. That's not required. It is one of the metric we needed. So R part predict is equal to predict HR R part comma type is equal to class. Table actual is equal to HR train df dollar is promoted, comma predicted is equal to R for predict. We got the confusion matrix. 50,069 plus 508 divided by 50,069 plus 71 plus false negatives are very high. 508. 92.28. Less than binary logistic regression. Coming. So library caret, confusion matrix as dot factor, HR train df, dollar is underscore promoted, comma, as dot factor, part predict, comma, positive, is equal to 1. So sensitivity specificity high, but positive predicted value is very low. Positive predicted value is very, very low. Similarly, if you are looking at mode, mode is equal to underscore recall. See, precision is very bad. Precision is worst. F1 score is also worst. Precision and F1 score both are very, very bad. Because of the imbalanced data, we are getting this problem. All right. So this is the process of running the decision tree in R. You'll get a statistical output, which is different from Python. In R, the summary function will give you detailed explanation of each and every node. A detailed explanation of each and every node is given in the summary. Here we have very less number of nodes. Otherwise, a detailed explanation is given for each and every node in the data. So the summary is very, very long in R because every node will be described. The tree will show less number of nodes. It will only show the important nodes. Whereas the summary output will give you the complete description of the tree. So this is the basic understanding of the decision tree model. We got 92%. The imbalance is affecting the data. Too many no's, very less yeses are there in our data, dependent variable. Right. So that is the problem. So this is the implementation of R part for classification. Now I wanted to implement it on regression, BigMart data. Open BigMart. Same thing. Up to here, it will be the same. Don't use as dot factor. Just use normal thing. No, we should not use. That we should use only classification. As dot factor. Decision tree library are part. Library are part dot plot. Big mart R part is equal to R part item underscore sales till dot comma data is equal to Big mart train DF. Summary, Big mart R part. Now you can see there are 31 nodes. Each node mean square error it is explaining. Up to node 15, they are very important. You can see each and every node is explained here. So the output starts from here. Summary, Big mart R part. So if I slightly scroll down, you can see variable importance. Item MRP is important. Outlet identifier is important. Outlet age is important. Visibility is important. Outlet type, item type, and item weight is important. Similarly, node number one. Node number one, that it's split on item MRP less than 143.5299. On to the left side, 4,296 observations. On to the right side, 4,227 observations. The condition is item MRP less than 143.5299. If it is yes, it's split into 4,296, this side 4,227. If I scroll down, node number 2, 4,296 on the left side were there, na? They split on outlet type. Outlet type, it's split on left side 539, right side 3,757. And then it again split on out. These are all sub branches of the tree. These are all the sub branches of the tree. So a detailed explanation of the tree will be given in the summary output. Now, if you want to see the visualization of the tree, we have to use R part dot plot Big mart R part. So you'll get the tree like this. This is the decision tree. Earlier we were not getting it, but here we are getting a proper tree. Yes or no, item MRP less outlet type is grocery store. Outlet identifiers 18 and 19. So you can see the tree left side, you can zoom it and you can see it. And the rules. Big mart R part. So these are the various rules for different item MRPs. So item outlet sales will be 207. Item outlet sales will be 207 when item MRP is less than 144 and outlet type is grocery store. The sales would be 207 when item MRP is less than 144 and outlet type is grocery store. The item outlet sales will be 471 when item MRP is greater than 144 and outlet identifier is 1019, then the sales would be 471. When will be there be higher sales? If you see the last row, the sales will be 5,669 when item MRP is greater than 177. Outlet identifier is 13 or 17 or 18 or 27, 35 or 45 or 46, 49, and outlet age is greater than 35. Then the predicted sales would be 5,669. This is the predicted sales. So this is how rules are created. These rules are created from the tree itself. And these rules are used for predictions. So you'll get repeated values. Unlike in linear regression, two values do not match in prediction. Here, the repeated values will come. Either you will get 5669 as predicted value, or 4117, or 3846, or 207, or 471. These only the predicted values. Right. So the predicted values will repeat because the rule's predicted value is fixed. Each rule's predicted value is fixed. Okay. So that is what it happens. So R part predict is equal to predict big mark R part, comma, type is equal to what is the predict dot R part. Type is equal to vector. Type is equal to vector. Head R part predict. So see, you got the predicted values. You can see 858 repeating 3 times, right? 471.31, 3845. So if you add more, you will see the repeated values. Because the rule has a fixed value, right? The rule predicts a fixed value. So that is why if that particular observation fits into that rule, the prediction will be fixed. Because the rules predict a standard value. See here, we have, see how many rules we have. We have only these 1, 2, 3, 4. So these are the set of the rules. The observations will fit into these rules. So the values will be predicted same because the set of rules are limited, right? How many rules we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 rules are there. So these 9 rules only will be checked for. For each set of observation, which rule comes near, that will be checked. If that rule matches more than 50% to that particular set of observation, the predicted value will be automatically assigned. The predicted value is fixed. The predicted value is fixed. That is why we have repetitions. Got it? So if you look at this, observation 2, observation 5, and observation 6, they fall with the same rule. So if you are looking at 2, 5, 6, sigma trained here, square bracket C of 2, 5, 6, the three rules, three observations have item MRP very close to one another, 48, 53, 51. Fat content regular, outlet similar, outlet size also similar. All of them are belonging to tier 3. And all three are supermarkets. So, and autumn outlet sales are also, only this has a higher one, but the rest of the three are closer. So there will be some similarity. So in this case, location type and type are matching, and visibility is also matching to some extent because two have zeros, right? So it will try to fit, all the parameters will not fit. Whatever fits into that rule, if it is more than 50% fitting, that assignment will be done. Now we have to calculate what for regression problems, root, mean, square, error. In carrot also we don't have. Let me check. Library carrot. We have MSc in model metrics. We have mean square error, SQRT, MSc of Big Mart trained here, dollar item outlet sales, comma, or part, library model metrics. So we got RMSE of 1102774. If you want to calculate RMSE manually, R part receipt is equal to Big Mart trained here, dollar item outlet sales minus R part predict. SQRT is R part receipt to the power of 2 with the same answer. So you can calculate RMSE either manually or you can use the model metrics mean square error. So we have not done the predict, right? R part test predict is equal to predict big mart R part, comma big mart test df, comma type is equal to vector. Type is equal to vector. Then write dot csv R part test predict, comma R part dot csv. Copy them into sample submission file and you can submit into the competition. And you can check your score. अभी जरूरत नहीं है. मतलब वो सैलरी सर्टिफिकेट नहीं है, इसलिए आपको कोई बंदा ने बोला कि नहीं होगा. बैंक अकाउंट में आता है लेकिन सर्टिफिकेट नहीं है. Okay, so supervised learning. So max step. So when you give the R part, parents, yeah. Control is there. rpart.control is there, no? There you have to give. In control is equal to max depth by default is 30. Okay, so you can add rpart, for example, for our data. Control is equal to rpart.control max depth is equal to 10. Okay, so this is how we can give the max depth argument. I think not much change in the data because our tree is smaller. It didn't go for 30. It is less than 30 only. So if you give rpart, I don't think there will be much change here. Max depth is equal to 10. We have given it as 10. So you can give it rpart.control is the one where you see the max depth. Okay. See, R is fully automated. You need not worry. In case of R, it is fully automated. It requires most of the arguments which their default are done by research. The programmers in R, what they have done is they have taken the statistical knowledge and they have fixed the parameters in R. Very rarely we alter the default parameters in R. Whereas in Python, they are open. We have to manually tune and all those things. In R, there's a lot of automation done by the community. Statistical softwares will have automation. Even SAS also has a lot of automation. So when you are dealing with R, there will be a lot of automation. There are a lot of input arguments which are default. The default arguments are set by the researchers or the developer based on their experience and knowledge. So we can still basically follow the default parameters in R. In Python, we have to manually set them because it's not a statistical software. It is a fine tuning is required in Python. But in R, we don't need to do that. We can follow the default parameters.
Research, is it easier in
grid search is easy in Python. So in R, what happens is we don't need to do grid search in R because the parameters are very easy to run. The time required for running these things in R is very fast and very easy compared to Python. Okay, so take for example this decision tree, the plotting and all, we are getting very fast, very easy right here, right? So R is comparatively easy to use. So grid search you can run. You can do the grid search. You have the grid search, cross validation, grid search plane. Everything is there. Whatever we have in Python, they are there in R also. But the requirement for those things is minimal because the R basic functions are designed in such a way by the researchers. The basic arguments are not simply just like that. They have done some research and kept the basic default arguments. So we go with those default arguments. And they keep statistics in mind. The R is a pure statistical software. So whatever they do, they keep statistical concepts in mind. Okay. So supervised learning, ensemble methods. Ensemble methods. So ensemble methods are multi-tree models. Ensemble methods are multi-tree models. In these multi-tree models, one of the models is bagging method, also called as bootstrap aggregating. Bootstrap aggregating or bagging method. The popular algorithm is random forest. The popular algorithm is random forest. In random forest, random refers to sampling method and forest refers to multiple trees. Forest refers to multiple trees. Random forest is a very popular algorithm under bootstrap aggregating method or bagging method, which is a multi-tree model or ensemble method. This is both a regression and classification model. This is both a regression and classification model. Step 1. Define the number of trees to be built. Trees to be built. Entry is 1000. Entry is equal to 1000. That means we are asking it to build 1000 decision trees. Step 2. Thousand samples of data has to be created using random sampling of 65% of rows or observations and square root of number of columns or variables per sample. 1000 samples of data has to be created using random sampling of 65% of the rows or observations and square root of number of columns or variables per sample. So each sample will not have all the observations. We'll only have 65% of the rows and square root of number of variables. If you have 25 variables, square root of 25 will be 5. If you have 16 variables, square root of 16 will be 4. If you have 20, square root of 20 will be somewhere around, so it will take 4 as the nearest point. If it is above 4.5, it will take 5. If it is less than 4.5, it will take it as 4. So this is how the thing. So another thing you need to understand is bootstrap aggregating. Bootstrap aggregating is a sampling method where data with replacement method is used. Whenever sample is randomly picked, sample is randomly picked, all the observations are considered. All the observations and variables are considered. Thereby, observations and variables will appear in multiple samples. So bootstrap aggregating is a method where whenever you are creating a sample, the whole data universe is considered, which means observations and variables in the previous sample will also have a chance to repeat in the next sample. So repetition will be there. Observations and variables will repeat in multiple samples. This process, we call it as bootstrap aggregating. Bootstrapping is where whenever a sample is being created, the whole data is considered. Thereby, observations and variables appear in multiple samples. That is what bootstrap. Because the more the number of times the observations and variables appear, the chances of correct prediction will be high. And it also overcomes the problem of overfitting. See, the reason why random forest was developed is to overcome the overfitting problem of decision tree. So, random forest overcomes the overfitting problem in decision tree. So, you won't see the overfitting problem occurring in random forest. Random forest was developed to overcome the overfitting problem in the decision trees. That is the disadvantage which is there in decision tree. To overcome the disadvantage, statisticians have developed the random forest model. Right? So the sampling is the critical part of the random forest algorithm. If something goes wrong in the sampling method, in the sampling step, the algorithm will fail. In the whole of this random forest algorithm, sampling is the most important step. Until the sampling process is done, the algorithm will not move forward. If something goes wrong in sampling method, the algorithm will throw up an error. And what is the most common problem? Memory size. Suppose your data is already 3 GB or 4 GB. You are creating 1000 samples means you will get somewhere around 6 to 7 GB as data. Now your laptop or a PC with 6 GB memory cannot handle such huge data. So memory size error will come because our system cannot process that huge data. For processing huge data, you might need a 12 GB RAM, you might need GPUs, you need a lot of infrastructure and all. So random forest, the biggest problem or the disadvantage is the memory size problem. If the data is very, very large. So this is suited for large data, but also requires large scale computing. Step 3. Once sampling is done, decision trees are parallelly built. One decision tree for one sample, same as the normal single decision tree. Just like your normal single decision tree will be built for one sample, one decision tree will be built. The splitting methods are again common. Gini is preferred. Entropy information gain is the other method. Gini is the default method. So once the sampling process is done, then decision trees are parallelly built. Parallel means each sample is independent. Parallel building of trees is possible as each sample is independent. There is no relationship between each sample 1 and sample 2. So there can be parallel decision trees will be built. So parallelization is one of the important concept of random forest. After bootstrapping, you need to understand parallelization of building of decision trees. Step 4. Prediction is also done for each tree, and based on the problem, if it is classification, majority voting, and if it is regression, average method is used for prediction. Is used for final prediction. Only disadvantage is computing power. It requires a lot of computing power. So just like your normal decision tree, it works with missing values, it works with skewness, it works with outliers, everything is there in random forest. But the only problem is the computing power. It requires large scale computing power. Okay. Now, for running this algorithm, I am running it in Big Mac cells. You need to install a library called Random Forest. Install package called Random Forest. No space, R small letter, F capital letter. Random Forest. Install. Library Random Forest. All right, all of you have installed BigMart RF is equal to random forest item underscore outlet underscore sales tilde dot comma data is equal to BigMart train deer comma n tree is equal to 2000 do dot trace they change the format why it is not coming random forest. Okay, so random forest formula data entry is by default 500. Weights replace sample size, node size, max nodes. Importance is equal to proximity, OVT, norm toes. Importance is equal to true. Comma, importance is equal to true, comma, do dot trace is equal to 100. So it ran for me print big mart RF. So R square is 58.04. Percentage variance explained is 58.04. Now RMSE. Yeah, we have calculated RMSE for the this one. Yeah, we have calculated. So SQRT of this. Got an RMSE of 1105. Slightly less. It's running for all of you. Yeah, it will take me. Every 100 trees, it is giving you output, right? We are getting 100 every 100 trees output, so that you can check the variance, whether there is any change is happening or not. Got it, all of you? Okay. All of you got the output? Still running. Okay. So we have built 2000 trees, right? So actually sometimes we don't need to build that many trees. Plot Big Mart RF. You can see here, this plot will tell you, I think after 500 trees only it is becoming a straight line, right? That means there is no change in the error post somewhere around 500 trees. So we can give maximum 500 trees as our number of trees. So the plot will tell us at which point of trees the error is becoming a straight line, right? So this will help us to reduce the computing power requirement. So based on this graph, it will tell us that 500 trees are enough. We don't need to give 2000 trees. We can just give 500 trees, because your computing guy, when you're deploying the model, they'll ask you, because it requires a lot of computing power. So what should be your preferable tree? We can say 200. In Python also, we can plot the error and then we can find it, or we can build a model in R, finalize the number of trees, and then implement it in Python. That is what we generally do. So this is one plot you need to understand. The second is variable importance plot. What are the important variables, right? So this variable important plot is also very, very important. So again, item MRP is very important, followed by outlet type, outlet identifier, outlet age, outlet size, and then these are all not important. Fat content, they're all 0, right? Weight and all slightly above 0. Weight, visibility, location type, outlet size, they are slightly above 0, right? But if you see these 3 points, they're on 0. So this is based on mean square error, increasing mean square error. This is based on node purity or Gini. Node purity means Gini. Based on Gini also, you can see here item MRP, but there is a change here. Outlet identifier is becoming important. Type followed by visibility, weight, type, and age. And rest of all are non-significant variables. This is based on Gini. Node purity means Gini. Based on Gini. So you can see the variable importance plot also, which is there in part of your. So you can say Big Mart RF dollar importance. You'll get the importance values. Similarly, a lot of things are calculated. RF dollar So a lot of importance values are calculated. So, but the primary plot is the variance plot and the tree plot. How many trees are required for our data? RF test predict is equal to predict big mart RF, comma big mart test DF, comma type is equal to we have to check predict dot random forest. So type is equal to response. Type is equal to prob or votes. Response is predicted values. So type is equal to response. Add RF test predict. So we got the predicted values. So these are the predicted values. Write.csv RF test predict, comma RF.csv. Any improvement in the score? All right. So if you want to see the specific tree, suppose I want to tree, get tree, big mart RF, comma, k is equal to, let us say I want to the 50th tree, tree number 50, comma label that is equal to true. So here, the 50th tree, the split variable is outlet type, then item weight, item MRP, item code, outlet identifier. These are the variables that are there in tree number 50. So if you want to see get a tree, big mart RF, comma k is equal to 75 tree number 75. It is based on outlet identifier, item code, outlet type, item weight, MRP, item type. So you can see here the trees, different trees, you can access them and see those trees here. So this is your 58th tree. This is your 75th tree. You can check the trees also, which tree, what, if you want to understand, you can check the tree also. Okay. implement it on HR, that HR analytics also, classification problem. So in HR analytics data, library random forest. HRRF is equal to random forest is, sorry, as dot factor is underscore promoted tilde dot comma data is equal to HR train df comma entry is equal to, this is large data, right? So 1000 is running, 1000 is running. Do dot trace is equal to 100 comma import is equal to true. See, precision is less, F1 score is less, but compared to decision tree, it is better. So prediction also, RF test predict is equal to predict RF comma HR test DF, what type is equal to class. Y.csv RF test predict comma RF.csv. Predicting on the test data and submitting it to the computation. Okay, all of you done? So I'll send this.